Hello. In this video, I will discuss bond polarity, overall molecule polarity, and covalent and ionic bonds, and how to determine covalent and ionic bonds whenever they are present in a molecule. So just to review, let's review what is a covalent bond. What is a covalent bond? This is formed by electron sharing. Remember that one bond is two electrons, and that sharing can be either by equal contribution of the two elements making the bond, or one bond will completely share. Now, that's not the major objective of this lesson, but I'm going to give you an idea of what I mean. So I'm showing elemental hydrogen with only its one valent electron. Okay, so when these two share their electrons to make a bond, we use fishhook arrows to move one electron where those electrons meet. Right there, that's where we're making a bond, and that bond is going to be called covalent. Now I draw the line to illustrate the bond. That bond is going to be called covalent because it came from sharing. Okay, the same thing can happen. Covalency can also happen with three hydrogens pairing up with the three valent electrons in nitrogen. So let's say you have those electrons that can bond. So again, fishhook arrows, when they meet up, where they combine, you will get a bond. So in this case, nitrogen is going to be in the middle, and then it's going to have two electrons that are not bonded, and then the other three will be shared with the hydrogens. Okay, this is another example of covalency. So if I am to show the bonds will be like this: three hydrogens going to a nitrogen with a lone pair. We have three covalent bonds that came from sharing. This molecule right there is ammonia. Okay, and then I can show you another example. So let's say fictitiously that you have a H and a Cl, and ammonia showing valence electrons again. If those two electrons are shared, those two electrons will be in there. You'll have three lone pairs out there, and you're gonna make a bond where they were sharing. Okay, that is for covalent bond. What about for ionic? If you want to make an ionic bond, it's gonna be usually between a metal and non-metal from the periodic table. The covalent bond is characterized by two non-metals sharing, no? But ionic will be metal and non-metal. I know we discussed this in earlier lesson, so I'm not gonna go deep into it. So let's say that you have a sodium. Sodium is in group 1. It will have one valent electron. There's a sodium right there. So let that sodium combine with a chlorine. Now, in this case, there is no covalency because metals react by losing, non-metals react by gaining. The sodium is gonna donate its electron onto the chlorine. Again, I'm using a fishhook arrow because we are transferring an electron, so one electron movement. So the sodium is giving off its electron. It will be one electron less. It's gonna form a cation, and then the chlorine just receive an electron that it doesn't naturally have in this periodic table. It's gonna be negatively charged. Negatively charged species are called anions. Now, this is one way we can explain, okay, where you have complete transfer of electrons, you get ionic bond. So like on here, we'll call it ionic. It's actually electrostatic. They are really not joined together by a physical bond, but by the charges, opposite charges attract. Up here, we have sharing. We have physical bonds right there. Now, apart from using this analogy, there's a scientist called Pauling that came up with a table of electronegativity values. We know naturally that electronegativity increases going to the right of the periodic table and going up. You'll see that fluorine has the highest number value of electronegativity. So Pauling says fluorine will have roughly an electronegativity of 4.0. Remember that electronegativity is the affinity for electrons by an atom. So like the atom liking to attract electrons. So it's just electron affinity. So think of it this way. An atom of an element is mean one's electrons. So usually, if we are to compare the electronegativity difference, which I would be calling it delta En, we should be able to predict the type of bond that we have between two elements. So if the delta En change in electronegativity between two elements is less than 0.4, we say that the bond is nonpolar and covalent. If it is between 0.4 and 1.9, we say that it's polar covalent. If it's greater than 1.9, the difference I mean, okay, then we'll say it's ionic. Let's test one for between H and H. So if you look at H and H, the electronegativity will be 2.29, 2.20. Okay, so I'm looking at the hydrogen. 2.20 minus 2.20, the difference delta En is 0. So I'm judging that that bond right there is nonpolar and covalent. Some people will call it pure covalent. If I look at the nitrogen here, based on the calculations, nitrogen has an electronegativity value, Pauling scale value of 3.04. Hydrogen is 2.20. If we subtract that, we'll get 4 and then 8, so 0.84. That bond is between 0.4 and 1.9. So we will call that bond here polar and covalent. That's the idea. For sodium chloride, chlorine has 3.16. We usually subtract the smaller number from the bigger number. Sodium has 0.93. If you do the subtraction of that, what do we get? Is it 3? So 3.16 and 0.93. We'll get 3 here. We'll get 2 and 2. So you get 2.23. That is a change in electronegativity difference. It's greater than 1.9. So we judge that the bond between sodium and chlorine is predicted to be ionic. That's the idea. Okay. So since you have ammonia having polar bonds, polar covalent bonds, we would predict, and the lone pair would predict that ammonia molecule itself is polar. So we are predicting bond polarity and eventual molecule polarity. And also, excuse me, the molecule is not flat, it's 3D. The dipole moments will contribute. So we're gonna talk about that now. So let's talk about ammonia just by itself. The Lewis structure of ammonia will look like this. We talked about molecular shapes. If you don't know about it, check the previous lesson. We say that according to Vespers theory, the bonds will be repelled. Valence shell electron pair repulsion theory. So this molecule ends up not to be flat, it's trigonal and pyramidal. Now, who is more electronegative? Remember, electronegativity increases across the periodic table and up. So according to our table right here, nitrogen, which is right here, seems to be more electronegative than hydrogen because it's further to the right, and you see that the Pauling number is higher. So we use dipole moments to point towards, we use an arrow to show dipole moments pointing towards the more electronegative element. What this tells us is that the electron density in this bond, because the bond is just a cloud, the electron density is closer to the nitrogen, which has high electron affinity. It will be partially positive. The nitrogen will be partially negative. The hydrogen will be partially positive. So this also will be partially positive. This will be partially positive. And you have those dipole moments pointing that way. You see there's a contribution there. The dipole moments, the direction of electron density is contributing, is going towards the nitrogen, so we always end up showing the net dipole. That net dipole tends to tell us if the molecule is polar. It so happens we do have a net dipole, so ammonia is indeed a polar molecule. Now I already did the calculations to show that the bond is polar. Even though I'm showing you charges on either end showing polarity, you can use Pauling scale to subtract the Pauling value of nitrogen minus that of hydrogen, and we said you will do 3.04 minus 2.20, and we ended up with 0.84 change in electronegativity, difference in electronegativity. That is one example. Let's look at another example. In this case, we are looking at H2O, which of course we know has a bent molecular shape and tetrahedral electronic shape. You will see that in a previous lesson. Again, oxygen is further to the right than hydrogen in the periodic table. Oxygen is right there. So we expect that the dipole moments will point towards the oxygen. Electron density is closer to oxygen than hydrogen. So this will be partially negative because the electrons are negatively charged, and if the electrons are farther away from hydrogen, hydrogen will be partially positive. So in that case, we say that the OH bond is polarized. And since they are contributing, we do have a net dipole right above the oxygen. And so we can already say that water is indeed a polar molecule. If you want to justify bipolarity of the OH bonds, just look at one of the sides, take electronegativity of oxygen minus the Pauling scale of hydrogen, and that again would be 3.44 minus hydrogen is 2.20. Our answer will be 1.24. Okay, you'll see that that is between 0.4 delta En is between 0.4 and 1.9. Our judgment is that those bonds, those OH bonds, are polar and covalent. There was sharing of electrons. Now, what if we have a molecule like CO2? What if you have a molecule like CO2? Again, carbon is behind oxygen. Remember again, electronegativity increases across the periodic table. There is carbon. So in this case, we have to subtract the electronegativity of carbon from that of oxygen. Okay, so, and we will say that oxygen is 3.44, but the electronegativity of carbon is 2.55, I believe. If we do that difference, 3.44 minus 2.55, let me punch in the numbers here real quick just to be accurate. 3.44 minus 2.55, the difference is 0.89. So that is again between 0.4 and 1.9. We can easily judge that the CO bond is indeed polar and covalent. So we point the dipole moment showing the electron density where it will be. We know that CO2 is linear. So you see how they are going on opposite side. There will be cancellation, because this is like, if you were to think of it, this is like positive 0.89, this is like negative 0.89. So there is no net dipole moment, and so CO2 is, even though it has polar covalent bonds, it's non-polar molecule. So for the fourth example, I'm going to give you an alkene. So let's say you have this alkene. I can tell you that the CF bond will be polar covalent. If you take the CF bond, fluorine is 3.98 minus that of carbon, which is 2.55. Okay, so 3.98 minus 2.55, I'm getting the difference to be 1.43. This bond right here and that bond right there, they are polar and covalent. Who is more electronegative? It's the fluorine. So the dipole moments will point towards the fluorine, Again, you have cancellation, such that if this is 1.43 by value, this will be negative 1.43. Overall, this molecule right here is non-polar molecule, even though it has polar covalent bonds. And then let's think of this other one that looks like this. This time my fluorines are on the same side. So if I point this way, you will see that there is a net dipole. There is net dipole right there. Okay, because they are going towards the same direction, upwards. So this molecule in this case would be a polar molecule. Sometimes you have what we call organometallics. So let's say you have this molecule right here, grignard, that is used later in organic chemistry. Really, it is the carbon that is bonded to the magnesium. So between the carbon and the magnesium, do we have partial charges? Let's see. So magnesium has a charge of 1.31, carbon has 2.55. So I'll say 2.55, that of carbon, subtract 1.31, that of magnesium. We are trying to determine if this bond is covalent or ionic. So I come to my calculator, just being careful. I can do it off head, but I don't take chances with chemistry. So it's 1.24 change in electronegativity, and that's between 0.4 and 1.9. So the CMG bond happens to be polar, and covalent. Where are the charges? The carbon will be on your right, so it's gonna be more electronegative. So I will point my dipole moments this way towards the carbon or this way towards the carbon. And so this carbon is partially negative, the magnesium is gonna be partially positive. This molecule, what we call the Grignard reagent, happens to be very polarized. And then for the last example I will give you, let's say that you have this molecule. Okay, so you see you have dipole moments because of more electronegativity of oxygen than the carbon. The Pauling scale value for oxygen is 3.44. That of carbon is 2.55. Again, if you do the difference, the difference between this is 0.89, like we did in CO2. Let's call this positive, and this going down was negative 0.89. There's no dipole moments because these are aligned. There's cancellation of dipole moments. So this molecule overall is gonna be non-polar molecule. So that's how you use the Pauling scale table and the criteria of judging polarity of the bond, a type of bond, whether it's nonpolar, covalent, polar, covalent, or ionic, to determine if you have polar bonds, and overall using the shape of the molecule and dipole moments to determine if the molecule is overall polar molecule or not. See you for another lesson next time. Bye.